Hi, let me tell you about another great Manning book, Bayesian Optimization in Action, written by Quan Nguyen.
Bayesian Optimization, BayesOpt, is a strategy for optimizing black box functions that are expensive to evaluate. It's particularly useful for hyperparameter tuning in machine learning, but its complexity often deters its widespread use. This book aims to simplify Bayesian optimization, providing examples, visual aids, and Python code to make it accessible and practical. Hyperparameter tuning exemplifies the need for Bayesian optimization. For instance, determining the optimal number of layers in a neural network is a costly black box problem due to the high computational demands and the uncertainty in performance outcomes. Bayesian optimization helps to efficiently select hyperparameters to achieve the best model configuration. Hyperparameter tuning is crucial in ML as it significantly affects model performance. The challenge is to find the best settings within resource constraints, such as time and computational power. Expensive black box optimization involves maximizing an objective function without knowledge of its internal workings. The high cost of function evaluations makes exhaustive searches impractical, necessitating more efficient methods like Bayesian optimization. Examples of expensive black box optimization include drug discovery, materials science, and resource exploration. These fields require optimizing outcomes with costly evaluations, making Bayesian optimization valuable. Bayesian optimization uses a predictive model to learn about the objective function, and Bayesian probability to decide where to collect new data. It consists of a predictive model, typically a Gaussian process, GP, and an optimization policy that guides the search for the optimum. GPs are preferred in BayesOpt for their probabilistic predictions and ability to quantify uncertainty, which is essential for informed decision-making. The BayesOpt policy uses the GP's predictions to score potential points, selecting the one with the highest acquisition score for evaluation. This iterative process forms a learning loop. The BayesOpt workflow involves training a GP model with an initial dataset, scoring points using the policy, and evaluating the highest scoring point. This cycle continues until the optimal solution is found. BayesOpt has proven to outperform simpler strategies like random sampling and grid search, especially in scenarios where evaluations are resource-intensive. BayesOpt is not recommended when objective evaluations are cheap and can be done extensively. In such cases, other methods may be more efficient. This book teaches the Gaussian process, GP model, and Bayesian optimization, BayesOpt task, including implementation in Python with tools like gPyTorch and BowTorch. It covers GP model visualization, parameter selection, extensions for large datasets, various BayesOpt strategies, specialized optimization settings, and real-life applications like ML model hyperparameter tuning. Real-world examples are used for practical understanding.
Get this book at manning.com